Alright, good morning. So, we have looked into the basic mathematical tools which I have explained to you last Wednesday. Now, just change this. I think I typed wrongly. Change it to x, please. Alright, we have learned about the expansion rule, and I taught you how we actually use it based on the reason that properties are stick functions and not half functions. So we will go to the next one, which is what we call the triple product rule. Now suppose you have enthalpy as a function of temperature and pressure. If you apply the expansion rule, you will get this equation here, right? Now, what if I differentiate this equation against pressure at constant enthalpy? So if I differentiate against pressure, what I'll get is dH over dP equals to blah blah blah, right? Now, see all this, please make the changes to your slides or to your notes. So what happens is, when I consider this equation at constant enthalpy, all these terms here, instead of being full derivatives, becomes partial derivatives. So now what I have is dH over dP is now 0 because constant enthalpy, right? So dH is equals to 0. And this term here becomes a partial derivative. And this is actually essentially equals to 1. Right? So at the end of the day, what you have is, at constant enthalpy, when you differentiate against P, you will get this equation. And if you rearrange the equation, alright, you get that all these three properties, when you rearrange it in different way, you get negative 1. Can you get that? So if your multiplication of partial H over partial TP, and partial P over partial HT, and partial T over partial PH is negative 1. And look, you can have P, 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 H, 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 T, T, and T. Alright, so do try on other properties as well, such as internal energy, Gibbs. You can try on Helmholtz as well if you want. So the next one is Maxwell's relation. So what is Maxwell's relation? It is a set of second derivatives of and their relations to physical properties. So from the fundamental property relations, which we have established in the first week, alright, you remember you get du equals to TdS minus PdV. So I can also write this U as a function of S and V in this manner, which is from the application of the expansion rule. So what you will find is that partial U over partial S at constant V is actually equals to T. If you look, du, du, ds, ds, dv, dv. So partial U over partial S at constant V is actually equals to T, and partial U over partial V at constant S is actually equals to negative P. So now, what happens if I consider a second derivative? That means, in this first case, I differentiate against V at constant S. Please change, there were mistakes in your notes because these two were interchanged, so please change it again back to whatever that is shown here. So, you start with partial U over partial S at constant V equals to T. If I differentiate this whole term against V at constant S, what do I have? I have a second derivative where this is a partial over partial V, alright, because you differentiate against V at constant entropy. Internal part is this, which is your initial partial U over partial S at constant V. What about this term? Now you have partial T over partial V at constant S. Alright, so For this one, we differentiate against S at constant V. So what do I have now? I have this term, alright, being differentiated against S at constant V, and this term will be negative partial P over partial S at constant V. Now, what happens is, why we are doing this is because this term here, partial, the second derivative of U against V and S at constant V and S, is interchangeable with this one. They are the same, basically, mathematically. So because these are the same, what you have now is partial T over partial V at constant S is actually equals to the negative of partial P over partial S at constant V. So now we have a second derivative equation. And you can now relate the change in temperature with volume at constant entropy to the change in pressure with entropy at constant volume. And these are the rest of the Maxwell relation. Can you try to prove all these yourself? That's the end of this lecture.